Today we are going to talk about curve sketching. Now we have done some curve sketching before, but it's been just the general shape for the most part. And so now we're going to take all of our calculus and put it all together to make detailed sketches of graphs. Okay, so these are just our basic steps, as we usually like to know what the domain is so that we're not skipping over something or missing a vertical asymptote. We find any intercepts if they're easy to find. We're going to look at asymptotes, and then these are the kind of the things we're going to focus on here is the intervals of increasing and decreasing and relative extrema, and then concavity and points of inflection. Okay, so when we do all this, there's a lot of calculus involved in this, and so instead of finding the derivatives and simplifying them and all, we're just going to work with them given to us. Okay, so there's a lot of effort that goes into finding these, but just for simplicity's sake, we're just going to use them as they're given to us. And I'll do that on the exam too. Okay, so that way we're not being tested whether we can do the derivative, but just whether we know what all of these things mean. Okay, so this is what we're going to graph. We have f, which is x times x minus 4 cubed, and then we have f prime and f double prime here. So these are what we're going to use to graph f. All right, so first of all, this is f is a polynomial function, and so there is no domain restriction. The intercepts are relatively easy to find. If I set this equal to 0, right, I have x times x minus 4 cubed equals 0. So that means x is 0 and 4 is 0. Oops. Actually, x equals 4 is 0, sorry. So that means I have 0, 0, and the point 4, 0. So I'm going to just put those on my graph while I have them. So I have a graph here started. So that means we have the origin here, and we have this point over here at 4, 0. So those are our intercepts. I don't need to look for a y-intercept, right, because 0, 0 is both. And if this is a function, it only has one y-intercept. All right. So there's no asymptotes, but we can talk about the end behavior here. Hopefully we remember that this a fourth degree polynomial has, right, this behavior. So technically speaking, we could write it as the limit as x goes to both positive and negative infinity of f is positive infinity, meaning that in both ends I'm going to have that up-up behavior. That's how we write it using calculus. And so now we will find our intervals of increasing and decreasing. So when I'm talking increasing, decreasing, and relative extrema, that means I'm going to look at the first derivative. So I'm going to set it equal to 0. Now the good news is that I have it all nice and factored, so no heavy lifting is required, right? I get x equals 1 and x equals 4 as my two zeros. I'm going to put them on my number line here at 1 and 4. These are my critical numbers, right? There's no places where my derivative is undefined because it's completely continuous. It's polynomial, and so is my f prime is also continuous. So if I plug in a value like 0, for instance, right, so I'd get negative 1 times positive 16 here times positive 4. So this will be negative. Right, if I test a number between 1 and 4, let's say 3. So this was when my test was x equals 0. So if I plug in x is 3, then this is positive, and this will also be positive because it'll be negative 1, but I'll have to square it. So this is positive overall. I check a number out here. Let's just say x is 10 is a nice one. That's positive. That's definitely positive. So I get positive, positive. All right, so that means that really this 4 here is nothing, right? It's neither. This is just, it's increasing from 1 to 4 and decreasing from negative infinity. I'm sorry, it's increasing from 1 past 4, right? It goes from 1 to 4 and then 4 to positive infinity where it's increasing. And then it is decreasing from negative infinity up to 1. Maybe I should just write that out. So if this is, I say this is increasing from positive 1 to positive 4 and also from 4 to infinity. Decreasing from negative infinity up to 1. Oops, that's my interval notation. All right, so then now based on this, then I'm going to apply my first derivative test. So here it does not change, right? So 4 is neither a min or max, but here I've got slope that's negative followed by slope that's positive, so I have a local minimum at 1. So let's write that. Local min at 1, f of 1. So while we're here, let's evaluate it at f of 1. Okay, so again, here's my f up here. So if I plug in, that's f of 1 is 1 times 1 minus 4, which is negative 3, cubed. So this is going to give me negative 27. So I have a point here at 1, negative 27 down here. All right, so let's put that on our graph. At positive 1. Did I say negative 1? I meant positive 1 if I said it. So I have positive 1, negative 27. I'm going to put that on my graph. Okay, so that's approximately, we'll say right here. And I'm just going to put this little piece on it like that so that I know it's a minimum. Okay. All right. So we're ready to move on to the next thing here. Right, so let's also find our intervals of concavity. So that means we're going to, whenever we say concavity, points of inflection, we mean f double prime, exactly the same procedure, just using f double prime. So again, I've got 0 equals, and my second derivative was 12 times x minus 4 times x minus 2, right? Again, I've got it all nice and factored, so I don't have to do any work. So I have x equals 4 and x equals 2 are my zeros of my second derivative. Putting them on the number line. Here's my 2, here's my 4. All right, so I'm going to test them in here. So if I test 0 out here, that's going to give me basically this 12 is always going to be positive, so I'm just going to kind of ignore it for right now. So when I plug in 0, I get negative 4 times negative 2, which is positive. Positive 12, then also positive, right? If I choose x equals 3 as a nice integer in between 2 and 4, positive, negative, positive, meaning it's negative overall. So this, now here when we're in second derivative, this means concave up, concave down, and then out here, if I choose a number like 6, this is positive, everything is positive. All right, so if I wanted to write my intervals of concavity, I would say that it's concave up at from negative infinity up until 2. Right, that's this interval here. And then from 4 to positive infinity. It's concave down in between there, between positive 2 and positive 4. So that makes both of these points of inflection. Now actually the 4 was an x-intercept, and so we already have that point on the graph. So I'm just going to mark it as a point of inflection there. I just put a little note up there to myself. And then I also want to figure out, because I need to put the other point of inflection, which is 2, on the graph. And so if I plug in 2 into f, right, I only go back to f for when I'm putting the point on my graph. So f of 2 is 2 times negative 2 cubed. So this is negative 8 times 2, which is negative 16. So I have the point 2, negative 16, and this is a point of inflection, POI for short. Okay, so we'll put this on the graph. 2, negative 16 would be about here. I'm just going to put a little I. Maybe that's a little easier than POI. All right. All right, so I have most of the important things on here. Okay, so what I'm going to do now is I'm going to condense my number line. This is going to make it a little bit easier for me to graph. All right, so let's look here at my two. What I'm looking for is these. So my critical numbers of my first derivative were 1 and 4, and my critical numbers of my second derivative were 2 and 4. So I'm going to put 1, 2, and 4 on my graph. So these zeros of my second derivative here, those are important. What I'm going to write here is in each section, I'm going to write the sign of the first and second derivative. So I'm going to write it in this order: f prime of x and f double prime of x. So between 0 and 1, so let's just put f primes on here to begin with. So let's cover up this part. Okay, so we're just going to put these on the graph right now. Okay. All right, so I just want to put the sign here. So out here, is, this one is, because it's negative, so decreasing up until I get to 1. So my first derivative here is negative, and it changes sign at 1, so on the other side it becomes positive. And then over here at 4 it's also positive. So actually in each, right, it doesn't change here. So my first derivative here is negative, positive, positive, positive in each one of these intervals. Okay, so this is what I put. Let me write them side by side here. Maybe that's a little bit easier. Maybe. There we go. That's a little bit better. Okay. So what I've done is I've taken the first derivative here, which is negative in this interval, and then I've just put, because each one of these I'm putting it in order. So these are my sign of my first derivative. It's only negative here, and then I just put it positive in all the other intervals. All right. So now we're going to put our concavity on there. So that's our second derivative. Okay, and so between up until 2, my second derivative is positive. So that means here and here, my second derivative is positive, right? So this is f prime, f double prime. And then at 2, between 2 and 4, my concavity is down, so it's negative. And then out here, it's positive. Okay, so this is going to help us graph. Okay, so this is going to help us make our graph. And just a reminder, in case I haven't said this before, but this is how my f prime and my f double primes interact. So I have sort of this little box, and so each one of these, so up here is f prime. This one means f prime is positive. This one says f prime is negative. Then f double prime is positive, and f double prime is negative. So when I get the positive positive, means I'm increasing and concave up, I get this shape, right? Concave up means that my kind of, if I think of it like this, it'll hold water, right? So, well, maybe not really water, but maybe a bean or something in your hand, okay? So that's increasing and concave up. So increasing and concave down means f prime is positive, f double prime is negative, looks like this, right? So concave down means your hand sort of has a downward shape to it, right? So then this one is f prime is negative, so, and f double prime is positive, so decreasing and concave down, or concave up. Maybe I'll write these. So this means it's increasing and concave up in the little box, right? This one is decreasing and concave up. This one is increasing and concave down, right? So that means f prime is positive, f double prime is negative, and then here I have f prime is negative and f double prime is negative. So this one is decreasing and down. So that's why I've written my pieces like this in here. All right, so we do know, maybe I want to put just one point on this other side over here. So there's my original f. So I know that my graph should end like this. We've already talked about that, right? So maybe I want to just plot a point over here. It's going to be a big point, I think. So just let me try -1. So f of -1 based upon this is -1 times -5 cubed. So that's positive 125. So that's like really way, 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 way up here. My graph is almost vertical in that spot. Okay. All right, so let me just draw some pieces here. So until I get down here to -1, or I'm sorry, why do I keep saying -1? It's +1. Then my graph is decreasing and concave up. Okay. So that means I have, my picture should look like this. Now my graph is going to be very vertical right here. I'm going to try to make that happen. So I know it's going to be up like this, and until I get down here to this 1, I am decreasing, means I'm falling, and I have to pass through that point, and there's my, so I'm decreasing and concave up. Okay. Now between 1 and 2, so that's between these 2 points, I am now increasing, means my graph will be rising, and concave up. So that means, again, I have now this picture here, increasing and concave up. So my graph should have that upward tilt until I get to the point of inflection. Now my graph should be rounded here. Okay? All right, so now between 2 and +4, I am increasing, but now concave down. So that means I have this picture here. So my graph is going to have a different kind of tilt on it until I get to this 4. So it kind of looks like this. Okay? It's hard to come up with polynomial functions that don't just behave all nice and symmetric. I kind of like these ones that have the interesting bend to them. And now I just have positive, positive. So that means I'm increasing in concave up. So like this piece here. So I probably should plot another point over here, but I'm not going to. So I'm just going to draw it up. Right? And so this is how we put it all together. We take our what we found out from the derivatives and we graph it very precisely. Right? So if I had just known the general shape of the graph, I could have drawn, I probably would have drawn something that looked a little bit more like a parabola, right? Because it's got the up with the 2 intercepts, but really this has sort of this extra little interesting bend to it. Right, so that is our first example. We'll do a more complicated example, I think, in the next one.